Hello, Calc students. There was this problem on the homework that I really liked as an example that I'm going to do here. And it's a good problem where I can show you a lot of the different concepts that we learned in section 3.3 and some in 3.1 as well. So it's a good one for me to go through. So I'm going to explain through some concepts. So you can use this to study. Hopefully you've already done this problem. And if you haven't, maybe this can help. Okay, so the goal here is to find the intervals on which f is increasing or decreasing for the function that's shown below. Find the local max-min values of f, and find the intervals of concavity and the inflection points. Okay, just for the sake of, so that I can explain some different concepts, I'm actually going to do these parts out of order, and you'll see why in a second. So I want to show you the first derivative test and the second derivative test. You can see from all the questions we're going to need the first derivative because we're looking at increasing and decreasing, and we're going to need the second derivative because we're discussing concavity. We're also going to need the zeros of those. So let's get all of that out of the way. Okay, so f prime of x is cosine x minus sine x. And f double prime is negative sine x minus cos x. Now, I'm actually going to do part B first, and I'll show you why. Let's find the max mins. Now, to find the max mins, we have two ways to do that. Now we're finding the local max and mins, so I'm not considering the endpoints, and I'm not looking for the absolute max and mins, although that's an interesting question too. So if I'm going to find the local max mins, I first need the critical values of f, so I need the zeros of f prime. So let's do that. I'm going to do f prime of x equal to 0, but what does that mean? That means 0 is equal to cosine x minus sine x, and sine x equals cos x. Now there's a couple different ways to solve this using precalc. One is just thinking about the unit circle. Where on the unit circle would sine equal cosine? Well, that means they have to both be the same sign, and they're both positive in the first quadrant, and they're both negative in the third quadrant. And the only time they equal each other is when you you have a reference angle of pi over 4. So this angle would be pi over 4. So our solutions are theta equal to pi over 4 plus pi k. Since they're a half turn, since these solutions are a half turn apart, it's plus pi k. There is another way to do this. I'll just make a note that I could divide both sides by cosine. And I can notice that. So you always want to be careful when you divide by a variable expression because you could be dividing by 0. But notice sine of x and cos x they don't have zeros at the same values. So x equals 0, pi over 2, 3 pi over 2. Those are not solutions to this. So you can divide by cosine x because we know cosine x is not 0. So sine x over cos x equals 1. This is, of course, tangent equal to 1. And tangent equals 1 at exactly these values. Tangent equals 1 at pi over 4, and the period of tangent is pi, so the solutions are this. Now, since our interval was we're only analyzing from 0 to 2 pi, then our critical values are. Our critical values are theta equal pi over 4 and theta equal 3 pi over 4. Oh, excuse me, not 3 pi over 4, 5 pi over 4. Okay, so we've got our critical values. Now, here's what we know. Now I'm going to come over on the right-hand side here. And in purple, we can find the max and mins without doing a sign analysis. we can use the second derivative test. And in this case, I claim the second derivative test is actually easier. So if we were just asked to find max and min, second derivative test is actually in a way more straightforward on this one. We already know that f prime of pi over 4 is 0. So now we just need to check, what is f double prime of pi over 4? Well, that is negative sine of pi over 4 minus cosine of pi over 4. And that is root 2 over 2 minus negative root 2 over 2 minus root 2 over 2, which is negative 2 root 2 over 2, which is negative root 2. The value there doesn't actually matter. What I care about is that it is negative. When the first derivative is 0 and the second derivative is negative, that means the graph is concave down. And at this critical point, the derivative is 0. Therefore, f has a max, I should say, relative or local max at x equals pi over 4. Okay, so that's the second derivative test. No sign analysis required. Let's do the second derivative test on the other critical value. The other critical value was 5 pi over 4. So what is f prime of 5 pi over 4? It is 0. What's f double prime of 5 pi over 4? Well, that is negative sine of 5 pi over 4 minus cosine of 5 pi over 4. And that is negative root 2 over 2 minus negative root 2 over 2, which is positive root 2. Negatives will cancel. I get 2 root 2 over 2. Those will cancel. But all that matters is this is positive. Therefore, the picture looks like this. I've got my critical point where I've got my point that is critical, and the tangent line is horizontal, and it's concave down or concave up at that point because the second derivative is positive. So f has a local min, sorry, not max, and has a local min at, I just realized I wrote ax. F has a local max at x equals 5 pi over 4, and f has a local min at x equals 5 pi over 4. All right, so max at pi over 4, min at 5 pi over 4. So that uses the second derivative test. So second derivative test, you just need to find the places where the derivative is 0. And if the second derivative is negative, it's max. And if the derivative is 0 and the second derivative is positive, it's a min. We've actually answered part B, find the local and max min values. Now let's do part A, find the intervals on which f is increasing or decreasing. Okay, so now I need to find so I actually have already found the critical values, so I just need to do a sign analysis of f prime. Well, my interval starts at 0, and my interval ends at 2 pi, and my critical values were pi over 4 and 5. I guess it would be more like here. Kind of like there, 5 pi over 4. That seems okay. So I could plug in pi over 6. I could actually even plug in 0. But we'll just avoid the endpoint. Actually, you can plug in 0. I'll plug in pi over 6. Let's see. So f prime pi over 6 is cosine of pi over 6 minus sine of pi over 6. And I already know that, oh yeah, sorry. I was going to say they're both positive, but that's subtraction in the middle. So cosine of pi over 6 is root 3 over 2, and this is 1/2. Root 3 over 2 is greater than 1/2, so this is positive. So that's positive. You also know that the cosine length, the x length on that triangle, is longer than the sine length. And now we want to plug in something in between here. Pi is very easy. Pi's in there. F prime of pi is cosine of pi minus sine of pi. Cosine of pi is, of course, -1. Sine of pi is 0. That is negative, so that's negative. And you're going to find that this is positive. It'll switch. You can check it. Actually, 3 pi over 2 is really easy. Actually, I'll do it. 3 pi over 2. 3 pi over 2. Cosine of 3 pi over 2 minus, sorry, that was a sloppy 3. Sine of 3 pi over 2. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is -1. That is 1, which is positive. Okay, so I did 3 pi over 2. So do you see how much more work the sign analysis of a trig function is? You got to plug in numbers. There's ways you could shortcut this, but I want to avoid some shortcuts at the moment. The second derivative test was actually faster for finding the local min maxes because I didn't even need to do this sign analysis. Okay, so here's my answer to part A. We have that f is increasing on the interval from 0 to pi over 4 and 5 pi over 4 to 2 pi because, I'll just put BC, because f prime is positive on these intervals. Okay, f is decreasing on pi over 4 to 5 pi over 4 because f prime is negative. We could just leave it at that. You don't even have to say on these intervals, but that's good enough. And remember, it doesn't matter whether you include the endpoints or not. Our book does not. Our convention is not to. Sometimes the College Board does. Doesn't matter. Okay. Now, notice we actually could answer part B again because we know that since we have our number line, since f switches from increasing to decreasing, then this is a max. Remember earlier we found that f has a local max at pi over 4. So now the first derivative test checks whether the first derivative switches signs. This was the second derivative test up here. Okay, so, and then also this would be a min because f switches from decreasing to increasing. So x equals pi over 4 is a local max because f prime switches from f prime being positive to f prime being negative. Let's say something kind of like that. And I could do the same thing for 5 pi over 4 with the similar statement. Part C. Part C, let's just finish this up. Part C was saying, find the intervals of concavity and the inflection points. Well, all we need is our All we need is our second derivative. Excuse me. I'm not sure why my tablet won't select. There we go. Just going to copy that. Let's bring that second derivative down here. And we just need to set this equal to 0. Negative sine x minus cosine x, and sine x equals negative cos x. And my favorite, you could divide both sides and figure out when tangent is equal to -1. My favorite way to do this is to just know your unit circle for these basic ones and just say, okay, what do I need? I need sine and cosine to have opposite signs, but they need to have the same magnitude, so they have the same value. Well, where's the only place that happens? When are they opposite signs? Well, that would be at these values. 3 pi over 4 and 7 pi over 4. Because, of course, this is negative root 2 over 2, positive root 2 over 2. So they one equals the negative of the other. And over here, it'd be root 2 over 2, comma, negative root 2 over 2. So they are the negative of each other. So they would satisfy this equation. And so now we just do, let's do it in green. F double prime, sign analysis, 0 to 2 pi. And we've got what? 3 pi over 4. And 7 pi over 4. Didn't quite put those in beautiful places, but that's okay. We can easily plug in pi over 2 is in here. Pi is always easy to plug in. 3 pi, sorry, pi is over here. Over here, we'd have to plug in something like, how about 11 pi over 6? So that would be over here. Okay, so we got to plug those into the second derivative. We'll do that in green. F double prime of pi over 2 is negative sine of pi over 2 minus cosine of pi over 2. And that's negative root 2 over 2 minus root 2 over 2. And that is clearly negative. So this is negative there. I'll just tell you that, and by the way, think about the graphs of sine and cosine. When you don't have anything squared and nothing shifted up, these are usually going to be zeros of multiplicity 1. So these the signs are going to switch. But that's not super obvious with trig functions, and there are cases where you can translate a trig function up so that just the bottom of the trig function just touches the x-axis. So it might not always be obvious that the signs here are just going to switch at every 0. So it's safest for you to just plug in those trig values and calculate it. Negative sine of pi minus cosine of pi, and this is 0 minus negative 1, which is 1, which is positive. So this is positive here, and 11 pi over 6. We expect to get a negative answer, but we'll just check. 11 pi over 6, and that would be what? Negative sine of 11 pi over 6 minus cosine of 11 pi over 6. And let's see, that is negative 1/2 minus cosine, minus, so the cosine of that angle is going to be root 3 over 2. So this is positive 1/2 minus root 3 over 2. Now root 3 over 2 is bigger than 1/2. It's greater than 1/2. So if I subtract root 3 over 2 from 1/2, this is negative. And so we have that the concavity is concave down. The f is concave down here because the second derivative is negative. So what would be our answer? Let's just squeeze our answer in over here. So for part C, f is concave up on the interval from 3 pi over 4 to 7 pi over 4 because concavity, I'll just say not concavity. Concavity switches, that's the reason. But you could just say because f double prime changes from negative to positive. Oh, sorry, from I'm sorry, concavity. I was thinking inflection point. I was actually jumping ahead. F is concave up on this interval because f double prime is positive. It's making that too hard. Let's see. So f is concave down on 0 to 3 pi over 4 and 7 pi over 4 to 2 pi. You don't need a union here. We're not solving an equation. We're just listing intervals where it's concave up and down. And the reason for this is, always give a reason, is f double prime is negative. So because, and this is true because. Okay. So that means we have an inflection point. So x equals 3 pi over 4 is an inflection point because f double prime switches from f double prime being negative to f double prime being positive. And we could just make the same statement for 7 pi over 4 because it switches from positive to negative. So we have inflection points wherever the original function is continuous and the second derivative switches signs.